Hello, everybody, and welcome to this month's edition of the SEG Women's Network webinar series. Today, we have Kathy Benison giving us a talk on salty secrets, comparing and contrasting evaporites on the surface and subsurface of Earth and Mars. If you have any questions during the time that Kathy is talking, please use the Q&A button down at the bottom of your screen, and we will get to the questions at the end of the talk. With the webinar formatting for Zoom, we can't actually have people unmute and speak. So we'll just do, I'll facilitate questions at the end. My name is Roxy Bush, and I'm glad to have you all here. Kathy is she is a professor in geoscience. Her dissertation at the University of Kansas was on Permian red beds and evaporites that formed in acid saline lakes. She was a professor at Central Michigan University for 15 years prior to becoming a professor of geology at West Virginia University in 2012. She is a GSA Fellow, an Explorers Club member, a science editor for geology, and a return sample selection participating scientist for the Mars 2020 mission. We are happy to have you on, Kathy. And now I'm going to go ahead and turn it over to you.
Thank you, Roxy. Can everybody see my screen, my title slide?
Yes, we should be good.
Okay. All right. I'm Kathy Benison. I'm very happy to be here today to have the opportunity to talk to you about one of my favorite topics, which is salt. I think that many geoscientists know the basics of salt. We know about bedded halite and bedded gypsum, but I think there are a lot of really intriguing aspects of salt and important aspects of salt for science and industry that maybe are kind of secretive. Not a lot of people know about them. So I designed this talk to highlight some intriguing aspects of salt. This photo that you see in the middle of this title slide is the end of a core, and we're looking at halite crystals, these cubic things that have grown in a red siltstone matrix, but they grew when the silt was still unconsolidated, uncemented, and they grew from a shallow, salty groundwater. We call both the crystals here and the lithology displacive halite, and displacive halite is really quite common and makes up a huge volume of evaporites, but we don't see it at the surface. We only see it in the subsurface, and you'll hear more about this in this talk today, this displacive halite. Before I begin, I wanted to acknowledge funding. I'm going to talk about some things that I've been working on for a long time. And so I've kind of dated myself here with the Phillips 66 logo. As a graduate student, I received funding for my research, which was really the start of this study of salt from Phillips Petroleum. So I received funding from them, National Geographic Society, Petroleum Research Fund, National Science Foundation, and more recently, NASA. I've also had excellent collaborators. Many of them have been students, and you'll see that they are cited with citations for published papers and abstracts throughout the talk. Evaporites, or chemical sediments, are in the subsurface, and they're very important. They act as stratigraphic traps. They act as marker beds because they can be seen easily on well logs. They make for excellent storage repositories. And more recently, we're finding that's even more and more important as we think about sequestration of gases in the subsurface. They preserve details about past environment, past climate, and past life. But it's challenging to understand them in the subsurface. How well can we recognize different salt lithologies and use them for industry and science? Well, an example of this challenge is shown here with these two slabs of halite. So on your left, you see a kind of a pink colored rock. This is bedded halite. And on the right is a very different looking rock. This is that displacive halite lithology. So these are both samples from the Triassic Mercia mudstone group of Northern Ireland. And I show them because they have really different looks and textures here, but they have approximately the same mineralogy. They both have halite, they both have a lot of hematite, they both have a little bit of quartz and a little bit of anhydrite. So if we just look at their composition, we really can't tell them apart. We really need the cores to see the textures, to see that they're different lithologies. So there are 4 salty secrets that I've divided the talk into. The first is that evaporites have a variety of crystal types, grain types, and lithologies. The second salty secret is that salts form at the surface, but are better preserved in the subsurface than in outcrops. Salt minerals trap remnants of past hydrosphere, atmosphere, and biosphere. And finally, salts exist on Mars and may inform us about past life on Mars. For most of this talk, I'll be using Permo-Triassic red beds and evaporites that formed in acid saline lakes and surrounding deposits as examples. So here's a map of Pangaea, and there are 4 symbols here to show the different rock types that will appear, the different rock formations that will appear in this talk. Much of it will be the Permian Nippewalla group of Kansas and Oklahoma, which I show with a red heart, because they're my favorites, my first love, my first salts. In yellow, in the yellow square is the approximate location of the Permian Opeechee Shale and the overlying Minnetonka limestone in the North and South Dakota. The blue star is for the Triassic Chugwater group and the Permian Goose Egg Formation of Wyoming. And then the green circle is the Mercia mudstone group of Northern Ireland. So these rocks all look quite similar, and we think they mean that there was this really regional scale, maybe continental scale system of acid saline lakes and groundwaters that made red beds and evaporites during the Permian and Triassic. So we can see these rocks in outcrops. When we see them in outcrop, typically the cap rock, the most resistant rock, is an evaporite. It's gypsum usually, as it is in this picture in the middle. And the red beds, which are a lot of siltstones and mudstones and some sandstones, are not very resistant to weathering because they're cemented by halite. So they form slopes. We can also see some of these rocks in some mines. This is Sophia Andesky, a recent PhD graduate from WVU, and she's looking at some the Hutchinson salts in Kansas in this mine. And then we have cores, and cores provide us a lot of great information. And we can see probably the best information about thickness of these rocks and their textures and chemistries in cores. But like all good sedimentary geology studies, we need to have a comparative analog. So a good comparative analog for those Permo-Triassic red beds and evaporites comes from some modern lake systems in Western Australia. So this photo I took from a plane. I was flying from Sydney to Perth and flew right over the field area. And this is part of the field area. So I like this photo because it shows different lakes of different colors all at once. And they're different colors due to their water depth and presence of water, their water chemistry, and what minerals they're precipitating. So the two dark lakes in the middle had recently had a thunderstorm go right across them, and they're in a flooded stage. But then we see other lakes to the north and south of them that have different colors. The yellow is lake water, the whites are halite and gypsum, and the red colors that you see are iron oxides that can precipitate directly from these lakes. So there's a lot of heterogeneity in these lakes from place to place at one time. But there's a lot of changes that happen through time as well as at any particular lake, where these lakes undergo flooding, evapotranspiration, and desiccation. And then wind can come along and rework those dried up lakes. So on the right, we see a lake at the top where we have actually Archean aged rocks sticking out, and they're coated with white salt, mainly halite here. And the water is a yellowish green because it is acid. It has a pH of about 2 in this picture. It's probably about 10 times saltier than seawater, and it has very complex chemistry with high amounts of dissolved aluminum in it that help give it that yellow color. On the bottom, we see a lake that's been dried out with just a salt crust here. So these are both dynamic systems through space and time. And they make a lot of really interesting looking evaporites. So here we're looking at, on the left, we have some gypsum from a lake, and you see these widening upward orange crystals. The crystals are actually orange because they have entrapped iron oxides and clays from the environment. In the middle is Joey, one of my former grad students, Joey Pritt, and he is holding a bedded crust of salts, and there's both halite and gypsum in this sample that he took from this lake that he's standing at. And then the lower right shows bedded halite, and the upper right shows both bedded halite and bedded gypsum. So we see different colors here and different crystal shapes. So there's a lot of variety here in the types of salts. So this brings us to salty secret number 1, which is evaporites have a variety of crystal types, grain types, and lithologies. This cartoon cross section shows a lot of different things. It's really showing different ways that salt minerals, mainly halite and gypsum, can form both at the surface and then the shallow subsurface. So it includes depositional and diagenetic features. So for right now, I want to point out 3 different depositional ways that we can find salts. The first is as cumulate crystals. So we see that there are these crystals that are either floating on the water at the water-air interface. Sometimes they join together to make these little boats, these little rafts. Sometimes they grow in the water column, and eventually they sink to the bottom. A second type of salt forms as bottom growth crystals. These form at the bottom of a surface water body like a lake or a lagoon, and they grow upward, and they tend to get bigger as they grow upward. A third type that we see is clastic chemical sediments. So if this lake happens to dry out and wind comes along and physically reworks, erodes these cumulates and bottom growth crystals, it can transport them and deposit them in dunes and other kinds of aeolian environments. And so we can see some clastic rocks that are composed of gypsum and sometimes even halite. There's a bunch of diagenetic features in here too. I'm not going to focus too much on those right now. So right now, let's think about the cumulates, the bottom growths, and the clastic. And we would call these bedded chemical sediments or bedded evaporites because they form at the surface and make beds. So here's some pictures of cumulates that are forming. On the left, you see my fingers for scale, and we're looking straight down into a little puddle of salt water at Death Valley. And these little cubic shapes are individual halite crystals growing in the water, and then they'll sink to the bottom. On the right is a picture I took in Western Australia, and we see that we're looking through about 10 centimeters of water here at a salt lake. And there are these white patches. These are these rafts that are made up of multiple crystals of halite that have grown together. One of the neat things about this photo is you'll see that some of these rafts have a shadow and some do not have a shadow. The ones that have a shadow are actually still floating on the surface of the water. The ones without a shadow have sunk to the bottom. So these rafts tend to form quite commonly in shallow salty waters. So these are both two types of cumulates. Bottom growth crystals are just what they sound like. They're crystals that start by growing at the sediment water interface, so the bottom of a lake or a lagoon, and they grow upward. So on the left, we see some gypsum crystals, and on the right, we see some halite. And in both cases, the place where I took these samples is shown in the photos above. And in both pictures, there's about 10 centimeters of salty acid lake water that these samples were growing at the bottom of. And finally, we have clastics. So if you've ever been to White Sands National Park in New Mexico, you have seen clastic gypsum. And so in this case, there are gypsum crystals that grow in a lake called Lake Lucero, and they get eroded and transported by the wind into dunes, and they make sand grains out of what were once gypsum crystals. So here's what they look like under the microscope, and they get cemented pretty readily by gypsum that's forming from groundwater, and they get turned into sandstones. These are some of the different diagenetic features that form from halite and gypsum. So we've got the displacive halite on the left. We're looking at cross-sectional views here throughout. So on the left is a core slab, and we're looking at that displacive halite is the kind of dark stuff that's growing in the matrix of the pinkish orange silt. Halite and gypsum also can form cement. So the second photo is showing a quartz sandstone with a very thin iron oxide cement, and then the rest of the intergranular pore space is filled with the halite cement. So there's a lot of halite in this sandstone. The third photo shows these long beds of these long vertical gypsum crystals. But these gypsum crystal shapes are now composed of halite. So these are halite replacement of bottom growth gypsum. And it's very common for halite and gypsum to replace each other. And finally, gypsum veins are shown in the photo on the right. So evaporites have a variety of crystal types, grain types, and lithologies. And if we know how to recognize those different crystal types and grain types and lithologies, then we can make interpretations about detailed depositional settings. So on the top here, we've got 3 types of bedded halite and gypsum. They all formed in a saline lake or different saline lakes. There are red clastics, and I didn't call these siliciclastics because some of these have quartz grains, but some have reworked gypsum grains, and they're red because they have iron oxides in them, and they form in desert soils and in dunes and in dry mud flats that are around these lakes. And in between those dry mud flats, sand flats, and saline lakes are saline mud flats. These are places where there is little vegetation, if any, and the groundwater table is quite high and is saturated with respect to salt minerals. And so this is where the displacive halite and also displacive gypsum forms in the saline mud flat, sand flat. So we can use these textures to tell us about depositional environments. Okay, salty secret 2 is that salts form at the surface, but they're better preserved in the subsurface than in outcrops. And they can be well preserved for hundreds of millions of years if they're in the right depth in the subsurface. So I'm showing you 2 pictures here. The one on the left is from Kansas. The one on the right is from Oklahoma. And they're both the Nippawalla group. And we're looking at the Blaine Formation, makes up the cap rock here, the whitish stuff, which is a bedded gypsum. And then below that is the Flower Pot Shale, which is has a lot of red siltstone here. When we look at these rocks, especially the bedded gypsum, the capstone rocks, we find that they're much thinner in outcrops than they are in core samples. So here on the left, on the top, we're seeing a picture of the Blaine Formation and outcrop sitting on top of the flower pot formation. And so the Blaine Formation at Lone Mountain in Oklahoma and in other Kansas and Oklahoma outcrops is only about 25 feet thick. So it's relatively thin for a formation. However, if we look in the subsurface at cores of these rocks, we find that it's much thicker. It tends to average about 125 feet thick. So much thicker in the subsurface than in the surface. Displacive halite is the most common lithology we see in the cores, and it's marked in these core pictures with the DH. So look at all the DH in here. This is a core from that goes through this section of the Blaine form. This is all the Blaine Formation here. In the outcrop photo, it's just this top light colored rock above the red. So we can kind of think about what happens between the surface and the outcrops for these rocks. In the subsurface, we see more lithologies. We see bedded halite, we see displacive halite, we see thicker units of siliciclastics that have halite cement. We don't see those things in the outcrops at all. So the hypothesis we have is that as these rocks get closer to the surface later in their life, there's alteration, mainly dissolution from meteoric waters that dissolves the halite. So how do we know that these outcrops had halite? Well, one thing we see is collapse structures that indicate late stage dissolution. And if you look carefully, if you're driving in south central Kansas and you look carefully, you see stuff like this. So in this outcrop, draw your attention to a sandstone on the left. We see it on the right, but instead of coming straight across, there's been a sinkhole that formed here. And so there's a lot of sinkholes and caves in this area, a lot of karst features that are due to late stage dissolution. We also, if we look closely, can see a lot of evidence of halite that is no longer there. So we see halite pseudomorphs, casts, and molds, and we find them in most lithofacies in the outcrop. So the picture on the top that has my finger here has all these triangles, and all of these triangles are now composed of gypsum and anhydrite, but they are in the shape of halite bottom growth crystals called chevrons. So we have evidence of halite that grew as bottom growth crystals. We also have evidence of halite that grew as cumulate crystals. If we look at just detailed descriptions that have been made for what these lithologies look like in outcrop and what they are in the core, we see they're quite different. So this table is showing you the Nippewalla group from Kansas, and we've got 6 formations in the Nippewalla group. The lithologies in outcrop show that these formations are fairly different from one another. So for example, the Blaine Formation in outcrop has mainly gypsum and anhydrite. And the Cedar Hill sandstone in outcrop has mainly sandstone and some mudstone. But when we look at those same rocks in core, we find that there's abundant displacive halite and bedded halite lithologies in almost all of these formations. The other thing to note is that in core, we note that the red beds, the clastic rocks, have cement that's halite and gypsum cement. So that makes us ask, how was the thickness affected by the dissolution of halite? If we look at thin sections and we do X-ray diffraction analysis to analyze the mineralogy, we find that almost all the lithologies of the Nippewalla group in the cores are the same. the same mineralogy. So bedded halite, displacive halite, quartz sandstone, gypsum and quartz siltstone, and gypsum siltstone all contain halite, hematite, gypsum, and quartz. Only the bedded gypsum is a little bit different. So what happens then if we dissolve this halite? How much red sediment would remain if the halite dissolved? We did an experiment. We took 6 different core slabs, all from one core in Kansas, and all from either the all from either the Flower Pot Shale or the Blaine Formation. And we carefully measured the thickness, the volume of each of these cores. We made a mold of each of the core because we had just about half the core. So this is the photo on the right here is a beaker where there's a piece of paper that's been made to there's a mold here. The volume where you see the red stuff is the same shape as the original core. So we took core and we put it in fresh water and we dissolved it. And then we filtered out the water. So we just had red sediment, just the sediment behind, and we poured it into this mold and we compared the measurements, both the weight and the thickness before and after, to see how much this thickness of this rock and volume of this rock was affected by dissolution. So this table is showing this, and there's 6 samples here. This number 6 is the sample that we just saw in the last slide. So this number 6 sample, we've got the depths in the core. So this was only about a 10-inch thick core. And so it was 22 centimeters in height and thickness before we dissolved it. After we dissolved it, the insoluble material, the red sediment, only was a height of 4.9 centimeters. So we lost a lot of height here, going from 22 centimeters to 4.9 centimeters. And we can also look at the weight and see how the weight has decreased. So the percentage of the rock lost to dissolution by height in this particular case for number 6 was 81.6% lost by height and 93.3% lost by mass. And we can look at our other 5 samples that we did in this experiment and see quite similar numbers. So therefore, a great volume and thickness of strata may have been lost to late stage near surface dissolution. And maybe this explains why the rocks in outcrop are so much thinner than when we see them in core. So the cores are the more complete stratigraphic record. And this is kind of opposite what we learn when we're learning field geology. We learn that the outcrops are where you're going to learn everything about deposition and you're going to have the complete record. But in the case of evaporites, it's really cores that have been well preserved. Salty secret number 3 is that salt minerals trap remnants of past hydrosphere, atmosphere, and biosphere. So here we're going back to the cumulate crystals, bottom growth crystals, and clastic chemical sediments that we talked about earlier. So there's a cartoon above for each of these. So the blue is supposed to represent water. The gray represents air. The white is the crystal that's forming, the salt crystal. And here I've modeled it after halite, but we could do the same thing for gypsum. So what we see is when a crystal is growing, a salt crystal is growing in water, there are not nice, flat, smooth crystal faces. There are all these little kind of stair steps that are dictated by the cleavage of the halite. If the halite is growing very fast, it'll grow around these imperfections, around these little divots, and it will seal in that water that it grew from in the form of a fluid inclusion. So we can see that there's already fluid inclusions that have grown as growth bands in this. Besides trapping the water, it will also trap anything else around. So the black bubble here is supposed to be an air bubble. The yellow circles and the red asterisk are supposed to be microbes. So sometimes microbes get trapped. And if the halite slows down its growth, it's not going to trap as many fluid inclusions. So this happens when the salt is growing rapidly. We also see the same thing in bottom growth crystals. And in this case, we can see these growth bands. And this is telling us some chronology. We know that this growth band at the bottom formed first, and the crystal grew outward from there. And so we can do some microstratigraphy with these fluid inclusions. But then remember that both cumulocrystals and bottom growth crystals can get reworked, and they can end up becoming grains in sand dunes and in sand flats. And those grains, though, even though they've been rounded, they're not a crystal anymore. They retain all the interior workings of the original crystal. So we can see growth bands with fluid inclusions. We can see solid inclusions. And so they are recording, even though they were deposited in this dune, they're recording the origin of the crystal in a lake. So this is a bedded halite core this is from the Nippewalla group of Kansas. And one of the things to call your attention to is the little thin white beds. There's one here and there's one up here. And these are composed of tiny, tiny crystals of various salts. And they form when the lake dries up. They're called an efflorescent crust. So they're evidence of desiccation. Below that, we see bigger, blockier crystals. So if we take this rock and we look at it under the microscope, this is what we see. This photo in the middle shows chevron crystal. So we see the dark and light bands here pointing up, making a chevron. The dark bands are composed of lots and lots of fluid inclusions. The clear bands have almost no fluid inclusions. So this is telling us that the halite changed how fast it was growing. It grew fastest during the day and slowest at night, and fastest during the day and slowest at night. So we can count these growth bands. Let's count the day bands: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's about 10 or 11 days of halite bottom growth crystal growth recorded here. The other thing that we notice here is that there is this dark stuff that we can't see through. This is one of those efflorescent crystal crusts, and we just can't see any light coming through because there's tiny, tiny salt crystals. And again, that tells us that the lake dried up. And then finally, we see this white patchy area, and this truncates the chevron crystal. So it is cut right into that chevron crystal. And it looks completely white to us here. It's full of salt. It's full of halite, but halite that grew very slowly as a cement. And this is telling us about flooding. So those three features that we see in this rock tell us that this came from an area where there was a lake that underwent evapoconcentration and then desiccation and then flooding. And if we look closely at one of these chevron growth bands, we see this picture on the right, and we can see that the cloudy bands have lots and lots of fluid inclusions. We would call these primary fluid inclusions because they're on growth bands, and they contain actual Permian lake water from when this was growing. When we look at these fluid inclusions, we always see water. So they've got the Permian lake water in them, but we can see other things. Sometimes they have little crystals. Those crystals could be crystals that grew from the lake water or that got transported into the lake water. Some of these fluid inclusions have microbes, and some have things that have blown in, such as silt. So this is quartz silt with a little bit of iron oxide coating on it. There are different ways we can test these fluid inclusions to learn more about environmental conditions. So I'm not going to talk too much about the method here, but but just give the results. So this is some data that came from a study of the Cedar Hill sandstone and the Salt Plain Formation, which both have bedded halite. They're both part of the Nippewalla group of Kansas, and they were taken from cores. And we were able to look at the homogenization temperature. That is a measurement of when a little vapor bubble disappears to liquid. And that tells us the water temperature. So these are measurements of the water temperature when the halite was growing. So each of the lines of black dots is a different bed. So for the Cedar Hill sandstones, we're seeing 1, 2, 3, 4 different beds of halite. And the little dots are telling us where in the bed and individual fluid inclusion temperatures. The red circles are the average for those beds. But then the thing to really point out here is that the red line, the zigzag line, is connecting the 4 maximum temperatures. So the maximum water temperature for the Cedar Hill sandstone was 73.7 degrees C. That's really, really warm. It's also a good proxy for air temperature, because in these environments, shallow water temperatures tend to be about the same temperature, within 1 degree, as the air temperature. So we can use these water temperatures as proxies for localized air temperatures. The other thing we can do, because we know we have day and night bands in these fluid inclusions, is we can see how much the temperature changes from day to night and from one day to the next. And that gives us a maximum diurnal temperature range of 32 degrees C. If we go to a desert, there's a bigger change from day to night in temperature than if we go to a humid environment. And so this maximum diurnal temperature range of 32 degrees C that we've measured for the Cedar Hill sandstone and the Salt Plain Formation tell us that this was a dry time. So it's both dry and warm. We can also use fluid inclusions to figure out pHs. And I know this is kind of a busy slide, so let me walk you through it a little bit. If we start with the diagram, the plot on the left, this is from some synthetic sodium chloride, sodium sulfate, sulfuric acid, water solutions, and fluid inclusions in halite that was grown for those standard solutions. And we then we do analysis with laser Raman spectroscopy, and that's a method that can detect covalent bonds in a liquid, a solid, or a gas. And so here we're doing it in these liquids, and we're finding that if the pH of the liquid is +1 or more, then we only have a sulfate peak. We don't have any bisulfate peak. If the pH is 0, we have a sulfate peak and a bisulfate peak. If the pH is -1, we have 2 bisulfate peaks, one on either side of the sulfate peak. Then we can go to the natural samples. These come from both the Nippewalla group and the Opeechee Shale, and these are measurements of fluid inclusions in halite. And I've color-coded here that the pink is on top of the sulfate peaks, and the blue is on top of the bisulfate peak. So remember, if we have 1 bisulfate peak, it tells us a pH of about 0. If we have 2, it tells us a negative pH. So we can use this to measure the acidity of these fluid inclusions. And we found that in all 92 fluid inclusions tested in the Opeechee halite, they all had a pH less than 1, and some had a negative pH. The Nippewalla group was not as acidic, where only 15% of 51 fluid inclusions had a bisulfate peak, with a pH indicating a pH of between 0 and 1. So these were acidic salty systems. We can also look at what we call daughter crystals in the fluid inclusions. And so the picture on the left is taken with cross-polarized light. The picture on the right is the same image with plane transmitted light. And then we've got the Raman data. So I want to call your attention to run 22, which matches up with the orange peak. So we were able to focus on that crystal and identify it as starkeyite. We were also able to focus in on another fluid inclusion, on another crystal where it says run 2 in green, and that's nitrojarosite. Now, nitrojarosite only forms in acid water, so that was really cool to find. The other spectra that don't have a mineral name all have a sulfate peak, and they all have a water peak. So there's some other kind of sulfate minerals, hydrated sulfate minerals. So this is a good way for us to get some refinement on the water chemistry. And then there are the microbes. So if we look closely, we can see microbes within these fluid inclusions. So we're looking into the crystals, into the fluid inclusions, and we see things like these yellow balls, which are Dunaliella algae. We see little bright white spots that are only about 1 to 2 microns in size, and those are prokaryotes, either bacteria or archaea. Under SEM, we see what look like cell division here. And we see these both in modern and ancient samples. So the picture with the brown circle, this is algae. And if we look closely, we see a little prokaryote, little pale green prokaryote here, and a yellow blob that is a carotenoid, something like beta carotene. Besides looking in plain transmitted light, we can also use fluorescence. So we have a UV light on our microscope, and organic materials will fluoresce. And so that's a helpful way to test for organic materials. This is one of my favorite pictures. So this is a fluid inclusion in halite, and we see 3 algal cells. They fluoresce blue, which is characteristic of the fluorescent response of algae. We see a little prokaryote here. There's actually more prokaryotes, but they're a little bit out of focus. But the one that you see here fluoresces green, and that's characteristic of bacteria or archaea. And then we have this yellow blob that fluoresces pink and purple, and that is beta carotene. And we can also use the laser Raman to analyze for organic compounds. So this yellow blob had this Raman spectra, which is characteristic of beta carotene. We can take our halite and gypsum and extract. We can basically dissolve them and culture them and find things like fungi as well. So there's lots of biological methods that can be done. Okay, so salty secret 4, we're on the lost salty secret. Salts exist on Mars and may inform us about past life on Mars. So we know that there's a lot of places on Mars that have sulfate salts like gypsum and anhydrite and some magnesium sulfate salts, but we also know that there's halite in places as well. This photo was taken by the Opportunity rover, and it shows 3 different strata. The bottom and top are cross-bedded sandstones, and the middle one is a mud-cracked mudstone, and all of this is sulfate minerals. So I think that this is something like a clastic gypsum. And even when we look up close with the different rovers, we see different textures that look like both depositional and diagenetic features. And again, a lot of sulfates here. So salt minerals on Mars tell us that Mars has a complex history of saline surface waters and groundwaters. And there's this rover, the Perseverance, which is part of the Mars 2020 mission, that has been drilling rock samples. And the plan is to bring them back to Earth in about 2 years. And for each workspace so far, the rover leaves it looking like this photo on the right, where there is an abrasion patch, where the rover has stripped off the weathering rind and has been able to analyze the chemistry and look at the texture of the fresh rock. And then there's 2 boreholes that are left and talus piles that are left when the core sample has been taken. And this, I know there's a lot on this slide. This shows you a quick picture of each of the abrasion pits that we've done so far and their matching core samples. So my favorites are up in the top right, Berry Hollow, Hazeltop, and Beer Wallow. And I really like these because these are composed of clastic sulfates with some sulfate cements. So I'm very interested in those. The cores are stored in this special little tube, and it looks kind of small. This is what the amount of rock would look like from one of these cores. So it's not a lot. And this can be horrifying to me when I really think about this, because when I go out in the field or I go to a core lab, I box up a lot of samples and send them back to my lab. So I have a lot of volume to work with. But then when I think about it, if you look at this picture of my finger, this is a little salt crystal. This is a large chip of halite for doing some of the fluid inclusion work that I showed you. So you really don't need a lot of volume of sample. And this gives me a lot of hope that some of these samples that get returned from Mars will have enough salt minerals that we can find some really interesting salty secrets in them. So just in conclusion, I want to repeat the 4 salty secrets. Evaporites have a variety of crystal types, grain types, and lithologies. Salts form at the surface, but are better preserved in the subsurface than in outcrops. Salt minerals trap remnants of past hydrosphere, atmosphere, and biosphere. And salts exist on Mars and may inform us about past life on Mars. So I really think that we will not have exhausted the question about is there life on Mars until we have salt samples back that we've been able to look at and investigate for microbes. Thank you very much for your attention.
Thank you very much, Kathy. This was fantastic. I really enjoyed listening to and seeing all of the different ways that, salt evaporates are related, both Earth and Mars. Again, if you have any questions for the other participants here, if you have any questions for Kathy, please put them in the Q&A box. I'd be happy to ask those of Kathy. While we're waiting for some of those questions to come in, I did want to remind everybody that we have another webinar in December to round out the year. And this will be a colleague of mine, actually, Emily McLean, is going to be talking about her foundation in geophysics and how that's applied to her career now in gas markets. All right, I'm not sure I don't see any questions yet. So perhaps there aren't any. In that case, Kathy, thank you so much for your time today. And we look forward to hearing some more about potentially past life on Mars and other things that you might have on the horizon then.
Thank you, everybody, for your attention, and thank you for inviting me.
Thanks.